Hi everyone, welcome to Vishwablooms. In this video, we'll be looking at Optics Class 8 Concept 4 Explanation. So, let's begin with the video. So, this Concept 4 actually deals completely about spherical mirrors. A spherical mirror is a small part of hollow sphere of glass. So here this is a hollow sphere of glass, and from this a small part is being cut, that is nothing but a spherical mirror. I hope it is clear. Now let's see the surfaces of cut part. So there are two surfaces of the cut part. So let's see one by one. First one is the bulged surface and other one is hollow surface. So let's look into the picture for better clarification. So this outermost surface, it is called as a bulged surface, and whatever is there inside, we call that surface to be as hollow surface. Now let's look at the types of spherical mirrors. So there are two types of spherical mirrors. The first one is concave mirror. If the bulged surface is silvered, then the hollow surface acts as the reflecting surface. So such a mirror will be called as concave mirror. So let's see the picture to understand it clearly. So here the bulged part is silver, that means you will not be able to see the image, and here we have the hollow part which is the reflecting surface. Fine, let's move on to the next type of spherical mirror, that is convex mirror. If the hollow surface is silvered, then the bulged surface acts as the reflecting surface, and such a mirror is called as convex mirror. So let's see the picture to understand it clearly. Here the hollow part is silvered and the other part, that is the bulged surface, is reflecting one. So in the silvered surface you would not be seeing the reflection. So these were types of spherical mirrors. So let's move on. Now we have something very important to learn about spherical mirrors. So this is very important because this is not only going to be beneficial for your 8th standard but also for your 10th standard. You will have this in your 10th standard also. Okay. So that's why please listen it carefully. It will be beneficial for your 10th too. So now the terms related to spherical mirrors is a topic. So there are actually many terms which we are going to see for spherical mirrors. First I'll tell you roughly what are all the terms we are going to see for concave and convex mirrors. Then all the terms we will discuss it one by one. Okay, I'll discuss that, don't worry. First I'll just mark it on the mirrors so that you will be familiar with the names at least. Okay, first, now this is a concave mirror and this is a convex mirror. You all know that. First we will see for concave mirror. Okay, now this is the silvered surface. So silvered surface, always you should remember, we will denote it in such way like this. Okay, so you can see that, right? Now this is something hollow inside and this is the, you all know, that is a reflecting surface, right? Now first this line I have divided, right? Yeah, so it is actually in middle of this mirror, that is called as principal axis. Remember the name, principal axis. That line is called as principal axis. Okay, done. That is the first thing you have to remember. Second and foremost thing is, here the point which is meeting both this mirror and principal axis, the point where these two meet, that point is called as pole. What it is called as? Pole. Okay, this is also important. The point where both the mirror and the principal axis meet, it is called as pole, and it is exactly in middle of the mirror. The point is exactly in middle of the mirror. Next, very important thing again I will tell you, that is called as center of curvature. See, the name is center of curvature. Now first, for telling this, I need to make you understand some things very clearly. First is curvature. So this is a curve, right? So curve is curvature. Now if I had to make this half part of the circle in a full manner, how would I do that? I would join this point to this point. Now this would be a circle. Now we all know that a circle will have a center. Now for this circle, if I join them exactly, as this is not a perfect circle, I may not get appropriate results. But if you will draw with a compass, you will get appropriate results. Now, the circle will have a center, right? So assume this to be the center for this, okay? Maybe this will be the center, right? Roughly I am taking, because this is not my perfect circle. So that is the center, right, of this curvature. That point is denoted with C, and it is called as center of curvature. And this pole point is denoted with P, okay? So instead of writing entire pole, you can simply write it as P. So how many we discussed? First principal axis, then center of curvature, and pole we discussed. Next is something very, very important. You have to understand it with concentration. So that's why I'll clear everything. So that is what I've denoted everything. Now something important I'll tell you. Okay, yeah. Now, as you all know, this is the reflecting surface. We all know this. That means it is going to reflect the rays whichever is going to come on it. Now, for the plane mirror, this is the, suppose here silver surface is there and here reflecting surface is there, right? Now if I send a ray over it like this, what will happen? It will come back like this. So similarly, even for concave mirrors also it is going to come back, but how it is going to come back, that also we have to see. Okay, first I will tell you this one. See, now I am going to pass one ray parallel to the principal axis. Now principal axis I will be using that word, then you should be able to understand that this is that line. Okay, now I have drawn one ray, I have emerged one ray parallel to principal axis. Then what is going to happen? Okay, let me emerge one more. Okay, parallel only. So this rays are parallel to principal axis. Now after reflection, what is going to happen is, it is going to go like this, cross. Okay, this is also going to go like that only. Now all the reflected rays are going to meet at one point, one and only point. Okay, that is called as focus. It is principal focus. It is denoted with F. Principal focus I have written here. Okay, so how it is, see, when rays of light, beam of light is parallel to principal axis, then after reflection it will appear to meet in one point. It actually meets or appears to meet in one single point, that is focus. Okay, so this is actually one law also, like for finding out sign convention and all that, and we will see that ray diagrams, it is important, this law. Okay, we will see in the next video, no worries. Okay, so that is the principal focus. So just remember one thing, where all the reflected rays will join and meet in one point, that point is principal focus. That's it, nothing else to remember. So I'll clear up this part so that it will look neater. So suppose this was the focus. Am I right? Let me mark it here, focus. Okay, next we have to see something called as radius of curvature. Okay, radius of curvature. So curvature, now for the curve we have to see the radius. So how do we see that? Now imagine this to be a complete circle. Now I have taken, this is the center, no? I told you I have taken it roughly because I wanted to show you very clearly. Now this is the circle. Imagine. It's not at all good. Okay, now this is okay. This is the center for this circle. This particular circle, this is the center. Now from center to the point to any point on the circle, is it not the radius? Yes, it is the radius, because if you take the circle also from center to any point on the circle, it is called as radius. So for this also, from the center to any point on the radius is radius itself. From center to any point on the curvature is radius. Okay, so remember this. So for a radius of curvature, how do you remember it? For radius of curvature, what we will say is the distance between the center of curvature and the pole, that is called as radius of curvature. Okay, definitions and all we will discuss it, but no worry, first you should understand where are the points and what is it, right? That's what. So from C to P, whatever the distance it is there, no, that is called as radius of curvature. Now I hope that is clear. It is denoted by capital R, not small r. Okay, that is nothing but radius of curvature. I hope this is also clear to you all. Now next thing we have to see is something called as focal length. So focal length. So the distance from the focus to the pole of the mirror, whatever that distance is there, no, that is only called as focal length. It is denoted by small f. Okay, small f is nothing but focal length. Clear? That's it. Focal length is this much. See, this from center to pole is nothing but radius of curvature. From focus to pole is nothing but focal length. That is clear to you, I am hoping it, and I am clearing it off. Then the next very important thing is aperture. Okay, now this is nothing but the distance, like the diameter enclosed between this circular portion. Now this mirror is there, right? From top to bottom, if you just connect that line, no, like this, if you do, this is only called as aperture. Okay, this is called as linear aperture. You will have angular aperture also, that is not there in your book, so no need to study that. Okay, linear aperture. Okay, so that is it. That is it. Just simple one, right? Just connect the corners, both the corners. The diameter is there. No, if you connect that, it is aperture. That's it. Okay. Next we have these two types of rays, that are paraxial rays and marginal rays. Now, if this is the principal axis, you all know, right? So first I will tell you what are paraxial rays. I will just write them here. Paraxial rays and marginal rays. Okay, first see, when we will pass some rays, right, we will send beam of light to mirror. It will come from focus, obviously, just now I told you. Now here also I am passing beam of light. It will pass through center, I mean focus. Now these rays, the beam of rays which are near to principal axis, are called as paraxial rays, and which are far from principal axis are called marginal rays. Now here, which are paraxial and which are marginal rays? See, I will change the color in order to make differentiation. This is there, no? These two. These are very close to the principal axis. So these are called as paraxial rays. Okay, these two. What are they called as? Paraxial rays. Next I will take another color. Yeah. Now these two are far from the principal axis, right? Far off from the principal axis, and they are called as marginal rays. So I hope this is also clear to you all. Okay. So these are only the terms related to spherical mirrors. I have shown only for concave mirror. Now we will look for the convex mirror. Actually, it will be very similar, but some differentiations will be there, obviously. Okay, let me clean this up. It's actually not so neat. Right. Then we'll move on to convex. There also we will have the same things only, but few new thing you will learn. This is a convex mirror. Okay. Now convex mirror, first and foremost thing, every time you have to start with principal axis. Right, so this is only the principal axis, this line, whatever it is there, same thing. Principal axis is the same here also. Okay, next here, next what we have to learn? Pole we have to learn. So here the point which is in between, like in the middle of the surface, is called as pole. This is only pole, P. Okay, these two are clear to you. Then now we have to see something called as principal focus. Let's see principal focus, or else first we will do center of curvature, then we will further move on to that. Okay, now this also will make circle like this, right? Yeah, this will also make some circle of this sort. Now this is also going to have some center, right? Now that center can be this, to that circle. Approximately I am drawing, maybe this is a center of curvature. Okay, So that's it. We all know this. Center of curvature definition I already explained you. Yeah. Next, radius of curvature, same thing. From the pole to center of curvature, what is the distance? That is only radius of curvature. Nothing new. You have already saw in the concave mirror. Right. Next, what we'll see is, then let's see focus, principal focus. Okay. So now here rays will go differently. Okay. So that now this is very important. Now I am going to incident few rays here. Two rays I am incidenting here. Now this rays will go like this. Yeah, like this. It will go outward. These rays. So these rays are parallel to the principal axis. Remember, they are parallel to the principal axis. Now when the reflected rays are extended backward, when they are extended backward, they will meet at one point. All the reflected rays will meet at one point, and that point is only called as focus. See, here also we had like that only, but here they went like this, no? Like, not like this, sorry. Like this. Okay. Similarly, here also they met at focus, but this is something imaginary. That means we have drawn it backward. We have extended it backward. Okay. Yeah, let it be. Now, this is the principal focus. That is also clear to you all. So the distance between pole and a focus is called as focal length. So we all know this, right? Nothing new in this. Small f it is denoted by. Okay. Next we have paraxial rays, marginal rays. Once again for this also I'll tell you so that you will not get confused anyway. So paraxial rays and I'll tell that. One second. I'll draw the rays now. Okay. Now see. Paraxial rays are rays which are nearer to the principal axis. So let me just write as PA. So this is very near to the principal axis and this is also near to the principal axis. So these two are paraxial rays. Now these two, the other two are very far from the principal axis. So these two are marginal rays. Okay. So that's it. I think we have covered everything here. Aperture, again this is the aperture. Same thing. Just connect that point to this point. That is the diameter. You can just connect it and have the aperture. So yeah, we have completed everything, right? All the terms have been completed for both concave and convex mirrors. So I hope you have got full clarity on this. Okay. Now I have one point to tell for principal focus. See. Here principal focus is in front of the mirror, in front of the reflecting surface. See, whatever is there back side of the mirror, we can't see, right? It is something imaginary, right? So remember, concave mirror is going to have real focus. Real focus it has. Because if something is there in front of the mirror, that only will consider to be real, right? Now, whereas if you see for the convex mirror, it is back of the mirror, it is behind the mirror, right? It is not in front, it is behind. So, this is a imaginary focus, or else it is not, you can just say it like this. Okay. Now, whereas this concave has a real focus. This is not a real focus, okay? Because it is behind the mirror, we cannot see it. Okay. So, that is what is all about the terms related to spherical mirrors. I don't think it is necessary to explain terms again because I've given the clear explanation of it. I think one last thing I have to tell is about normal. Okay, normal. See, now here we have incidented one ray and it is going through the focus. Now from this point where it is intersecting on the mirror to the point on to center of curvature, this line is called as normal. Okay. So for both the mirrors, it is like that only. I forgot to tell you all. I'm telling it now. Okay. Now for concave also, I am sending one line like this, like this. Sorry. Direction is very important. I am connecting it to the focus. Now here also you will have it. Okay. Connected that in between the incident ray, you will have connected to center of curvature. Okay, yeah, this is only normal. We have to learn the relationship between the focal length, that is f, and the radius of curvature, that is r. Okay, so now what is focal length? The distance between focus and pole, that is focal length, and the distance between center of curvature and pole is radius of curvature. So this you know, I hope, right? Yeah. So next we are going to find out a relationship between them. How do we do that? First, for that I have taken one concave mirror here, as you all can see. Then what I did is I have taken the principal axis here, and then I have taken a beam of light, that is AM. So AM is parallel to CF, so sorry, CP. Okay, remember that I have taken a beam parallel, and obviously the reflected ray M will be it will be, you know, meeting at focus. So MF is the reflected ray and incident ray is AM. AM is the incident ray. Okay, now this is clear, right? Now then what I have did is I have connected the point of incidence and the center of curvature. Okay, point of incidence and center of curvature, that is nothing but normal. I have already explained, right? Yeah, so now I have connected the normal also, that is MC is normal. Okay, now we all know. Now is something important, so I'm going to erase everything and write it clearly for you all. So from the first law of reflection, what does it state? It states that, yeah, correct. So angle of reflection is equal, angle of incidence is equal to angle of reflection. This is only stated by the first law of reflection. Now by that we can say these two angles are equal, because this is the angle of incidence and this is the angle of reflection, right? So what do we say is angle AMC is equal to angle CMF, right? So this is from the first law of reflection, that is theta is it is assumed already, let it be. Now I told that AM is parallel to CP, okay, and MC is normal. Now if you consider MC to be a transversal line between these two parallel lines, what would be it? See, AMC, this angle will be equal to MCF. This angle and this angle will be equal. Am I right? Because they are alternate interior angles. Alternate interior angles. So let me write it here in this step. That is, which angles? Angle AMC is equal to angle MCF. Okay, that is due to the alternate interior angles. Okay, so I have just written in short forms, but you need to write it completely. Now AMC is common, right? See, when something is equal to both these things, these two are also equal only, right? So angle CMF is equal to angle MCF. Angle CMF, this angle is equal to MCF, this angle. That's all, right? That is only we have shown. See, sorry, MCF, this one, MCF, this angle, and CMF, these two angles are equal. Clear? See, this angle, I'll erase and tell you that two angles. See, CMF is this angle, MCF is this angle, MCF, this angle. Okay, now I'll tell you this angle, this angle and this angle are equal. That means if any two sides of a if any two angles of a triangle are equal, it means that the triangle will be an isosceles triangle. So triangle FCM will be an isosceles triangle. Okay, it is an isosceles triangle. So you note until till here. Okay, until here you just note it. I'll erase everything, so that is clear to you. Okay, so the point lastly we concluded was angle CMF is equal to angle MCF, and we also stated that triangle FCM is an isosceles triangle. Okay, these were the two conclusions which we have stated just now. Okay, now see, FCM is a triangle. Now there is one property of triangles. Okay, maybe you will not know it this year. In the next 9th standard CBSE book you will be having this actually. Now when these two angles are equal, it is said to be an isosceles triangle. Okay, now generally you would study it as when two sides are equal, it is an isosceles triangle. When two angles are equal also, you can say it as an isosceles triangle. And remember, there is one theorem, actual theorem statement, which states that when two angles are equal to each other, then their opposite sides are also equal. Okay, for this opposite is this, for this opposite is this. That means these two sides are also equal, it will state. Okay, suppose if this is ABC, now if angle ABC is equal to angle ACB, this means that AB is equal to AC sides. Okay, so that is one theorem, you will learn it, but I am telling you because I have to explain the next part. Okay, yeah, so let's go back. So as we said that angle CMF, this one, and MCF, these two are equal, opposite sides are also going to be equal, that is FC and MF. Am I right? So FC is equal to FP. MF for FM. FC is equal to FM. I have marked it here also. Okay, now why this is because of that theorem which I have explained. Okay, yeah. Now these rays are paraxial. Obviously, this is very near to principal axis, so this is paraxial rays. Now in paraxial rays, remember in paraxial rays, this FM and this FP, both are nearby, right? Like they look to be similar. It is, as it is very close, M is very close to P, right? So this is close, right? So we can assume, like we can say that FM length is similar, is very near to FP. Almost equivalent means you will show this sign. Okay, like this. Okay, you cannot say equal, but you can say similar or almost the same. So when I said that FM is similar to FP, see here also we have FM, here also we have FM. So that states that FC is equal to FP. The other two you can equate it, right? When something is equal to one value, the other two also we can equate. Okay, that only I did. Okay, nothing new. So FC is equal to FP, I concluded from this. Okay, now FC is nothing but it is like the half of CP. Your full CP, from that half is FC. Okay, from that half of CP is equal to FP. Now here something is we have to observe. FP is nothing but focal length, right? So focal length, F is equal to CP is nothing but, what is CP? Here CP is radius of curvature. So half of radius of curvature. You can also write it as, if you send this half to LHS, R is equal to 2F. So these are the two conclusions. Like focus is half of radius of curvature. This is only the relationship between it, and we have shown the detailed explanation also. Thanks for watching our video. Do like, share, comment to our channel, and don't forget to subscribe it. Hit the bell icon. See you next time. Bye bye.